Hello. Today I'm going to introduce a concept called Ostwald ripening. So let's just write it down. So what is Ostwald ripening? Well, imagine we've got two bubbles. I'm going to have a small bubble, say a sphere of radius RA, and then over here I'm going to have a larger bubble, which I'm going to give a radius RB. And these will be bubbles of a phase that I will label phase 2. And phase 2 for today's discussion will be a gas. So that can be hydrogen or carbon dioxide or natural gas. And of course, we're going to be looking at those gases stored within a porous medium. So between these two bubbles is another phase 1, and that will be the aqueous phase. That will be water or salty water brine. Now imagine these two bubbles can't actually move, and of course that's obvious, they're going to be trapped within the pore space. But now let's think carefully about what happens if some of the gas can dissolve in the aqueous phase. And I'm now going to analyse that process, and I'm going to do it by using a series of physical laws. So the first is Henry's law. Now, Henry's law says that the amount of gas that can dissolve in the aqueous phase is proportional to the pressure in the gas. So we can write that the concentration, and that's the concentration of dissolved gas in the aqueous phase, is a constant, which is Henry's constant, given with an H, times the pressure in the gas, which in this case is P2. Before we go any further, let's get units sorted out. Everything is going to be strict SI, of course. So pressure is measured in pascals. There are lots of ways in which concentration can be defined. It turns out, for the argument we're going to present today, it's easiest if C is defined as moles per cubic meter. Per cubic meter, right? Strict SI. No litres hanging around, otherwise we're out by a factor of 1,000. So that's Henry's law. But just a moment, let's look at this. What is the pressure in these gases? Well, phase 1, the aqueous phase, we assume is continuous, and that has, if there's no flow, a constant pressure, which we can call P1. What is the pressure P2? Well, now we invoke another law, which we have addressed before, is the Young-Laplace. And if we have a spherical bubble, I agree that's an idealization, then P2 minus P1 is the capillary pressure, and that's 2 times the interfacial tension between the two fluids divided by the radius. Now, what are the implications? This bubble has a smaller radius, which means that the pressure difference between it and the aqueous phase is larger than it is for the big bubble. And then from Henry's law, this means that P2 is higher here than here. So P2 for bubble A is greater than P2 for bubble B. So this means now, if we consider dissolved material, which I'll give with a different colour here, there's more dissolved material here than here. So there's a concentration gradient. So at this point, we're going to invoke yet another law, which is Fick's law. And again, we've introduced this before. Fick's law of diffusion says that there is a diffusive flux which is proportional to a pressure gradient. And this is the diffusion coefficient. So what it says is that because the concentration is higher here than here, that there will be a diffusive flux of material from here to here. So what happens? Well, of course, this bubble starts to dissolve and get smaller. Material is moving here, and when it exceeds the solubility, of course, material will move into the big bubble. So the big bubble will get bigger, and the small bubble will get smaller. And when that happens, now this radius gets even smaller, this pressure drop gets larger, there's even more stuff being dissolved, there's an even greater flux. So you can see this is an unstable situation, and eventually the little bubble disappears and the big bubble gets bigger. And that process is called Ostwald ripening. Now, if we had bubbles essentially just in a liquid with no porous medium, of course the end result would be there's just one big bubble. That's the position of equilibrium. But we're interested in flowing porous media. So it's a little bit more subtle than that. So let's imagine a similar arrangement where we're injecting water to displace gas. This can happen because you're injecting water. This can happen as natural water influx as gas is produced from a field. So what does that mean? Well, during the water flooding, imagine that we initially trap a relatively small ganglion of gas now within the pore space. And its radius of curvature, we can again call it Ra. But we could also, later on during the displacement, trap another ganglion of gas, and its radius of curvature, its average radius of curvature, we can call Rb. They're going to have a more complex geometry. The same process occurs. We will still have more material dissolved than here, and there will be a diffusive flux. However, that doesn't mean to say that this big bubble is now going to expand and this is going to shrink away to nothing, because clearly, if we think about a porous medium, as this big bubble begins to expand, maybe it has to expand through a narrow throat. And to do that, it needs actually a much larger capillary pressure, a much smaller radius of curvature. So in a porous medium, it's quite subtle, this Ostwald ripening process. There will be a tendency for some smaller ganglia to shrink, the ones that are trapped at a high capillary pressure. And there will be a tendency for some of the larger ganglia that are trapped at a lower capillary pressure to expand. So there will be rearrangement in the pore space, and indeed some ganglia, and we see this experimentally, can completely disappear. However, it's a rearrangement within the pore space. It's not necessarily everything goes into one big blob. That doesn't happen. We still get lots of blobs of different size. So what we're going to do now is we're going to do two things. One is we're going to estimate the time scale for this rearrangement on the pore scale. How long does it take? Is it going to take a few seconds? Is it going to take hundreds of years? In which case, I suppose we might think we can ignore it. So that's the first thing we're going to do. And then the second thing is we are going to explore the consequences for transport when we take account of Ostwald ripening, and particularly this subtlety of what actually does happen. Do all the small ganglia disappear? Do the big ones get bigger? What does that actually mean? So we will do both. But let's first look at the time scale. So we've invoked these three physical laws. I'm going to invoke one more, and it's a nice exercise in physics, and then we can just go through the estimate of what the time scale is. And the last law we're going to do uses the ideal gas law. Because we've got concentration in moles, so we need an equation with moles to get some idea of how long does it take for those moles to dissolve. So this is pressure, this is volume, N is the number of moles, R is the ideal gas constant, and T is the absolute temperature. And what we're going to do in our analysis is we're going to assume that the gas obeys the ideal gas law. That may not be the case. If you're worried about it, you can do exactly the same analysis with a Z or a Z factor in there, but we're just going to keep it simple. So we're going to use these four rules, and we're going to use those to analyze the time it takes for there to be significant rearrangement in the pore space. So we're going to introduce a characteristic curvature, R, and we're going to introduce a length scale, L, over which the process occurs. So we can imagine several ganglia within the pore space, like this, And we're going to imagine several ganglia in the pore space over some length, which I'm going to call L. Okay, and that's going to be of order of pore size. So without giving anything away, it's going to be about a millimeter. Okay, so when we sort of look at several pores. Then we're going to look at a typical radius of curvature, and we're going to look at a typical capillary pressure, a typical pressure difference between the phases, which is obviously going to be of order 2 sigma divided by R. So how are we going to do this? Well, what we're going to do is we're going to look at the diffusive flux and find the time necessary that this diffusive flux would be sufficient to rearrange the gas within the pore space. And by rearrange, I'm actually going to look at, well, there's a diffusive flux that basically moves as many moles as there are moles of gas in the system to begin with. So in many ways, it's a sort of overestimate of the time, because the rearrangement is quite subtle. It's not that everything dissolves and everything grows, but at least it allows us to get an order of magnitude. Okay, so now we'll get to the calculation for a typical time scale for there to be significant rearrangement of the ganglia over some length scale L. And I'll just draw this schematic of a few trapped blobs again so that it's clear what we're talking about. Okay, so this will be our length L. So what's our diffusive flux? That's Fick's law again. And I'm just going to do an order of magnitude estimate. So at this point, I'm just going to do approximations, roughly speaking, right, rather than anything precise. So this flux will be of order, a diffusion coefficient, a change, a difference in concentration between a blob which has a small radius of curvature and one that has a larger radius of curvature, and the length scale is L. So now I need to know what this delta C is. Well, if we have Henry's law, which says that C is H times the pressure in the gas, then the difference in C is going to be H times a typical difference in pressure between the two ganglia. Well, that's driven by capillary pressure, and we know that PC can be written as 2 sigma over R, where R is the mean curvature, or mean radius of curvature. So what's a typical difference? Well, a typical difference, say between something with radius RA and something with radius RB, okay, would be the change in PC, which is equivalent to the change in the pressure in the gas, will be 2 sigma 1 over RA minus 1 over RB. Well, that becomes a bit complicated because what's RA and RB? So I'm just going to put in, roughly speaking, that this is of order sigma divided by R, which will be a typical radius of curvature of a meniscus, and that will be related to a typical pore radius. Okay, so this is order of magnitude. You know, what's happened to the two? Maybe there's a difference here, just to get a scale. Okay, it's not a precise calculation. So the change in C is approximately of order Henry's constant times the interfacial tension divided by what is actually going to be a typical pore or throat radius. Okay, so we got the flux, we got that, so we can put that in the equation here. So that's dH okay. So now let's think about some units. Right, it's always useful to get those units right. So the flux is in moles per square meter per second. Okay, that's why we need to do cubic meters for C. Okay, so the total flux over a time t is going to be F times t times area. And of course, the length, we're going to assume a cube of length L. So that's typical distance is L, typical area is L squared. And we're getting to it. Typical volume will be L cubed. It's just scaling. Okay. So we can put that in. Okay. That's going to be approximately, just put these in. There's an L squared here and an L here. So actually an L is going to go up at the top. Okay. So there's a time, which is what we're going to estimate. There's a dH sigma L, and that's going to be divided by R. Okay, so that flux, what does that have to be equal to for a significant rearrangement? Well, the idea is how many moles of gas are in a volume L cubed to begin with. And if the flux is this total flux, which is now measured in moles, is equal to that total moles, then there's been plenty of time for the ganglia to rearrange. Okay, so what we have is we've got a volume L cubed. How much gas do we have in that volume? And virtually all of the moles of gas are actually in the gaseous phase. I know some's dissolved, but actually that's a small contribution. So just let's look at how much is in the gaseous phase. So the volume of gas is going to be L cubed times porosity times the gas saturation. And when we're talking about blobs of gas being trapped within the pore space, then this is going to be the residual gas saturation. This is actually going to be gas that's trapped and the blobs are rearranging. They're not connected and flowing, because when they're connected and flowing, they can reach equilibrium a lot easier. So what we're talking about here is that the ganglia will rearrange until actually each ganglion locally has a radius of curvature that is equal to every other ganglion, even though they're disconnected in space. And that's basically where the ripening reaches equilibrium. So that's the volume of gas. So that's your volume of gas. But now we need to invoke the ideal gas law, don't we? Right? Which is P, the volume is the volume of gas. This is the absolute pressure. Okay, so it's not the capillary pressure, it's actually the absolute pressure that's being imposed on the system. So PV is nRT. So the number of moles of gas is equal to P. Then I'm going to put in this volume, L cubed phi SGR. Okay, N is PV, and then divided by RT. So we now have a time scale, which is when this flux, which is now measured in moles, is equal to this. So the time for significant rearrangement is when I equate this object with this object. So let's just write down what we had before. The number of moles that is within a length L is PL cubed porosity SGR, and then we need to divide that by RT because we were using the ideal gas law. And then the total flux over a time t, and that was measured in moles, so it's the change in the number of moles that is possible because of the flux, is proportional to time, the diffusion coefficient, Henry's constant, interfacial tension L over R. And what we're going to do is we're going to equate those two. So we're going to assume that basically the total flux is large enough to have moved all the moles around. Okay, so now we're going to find T. So we're going to put these two equal and we're going to find T. Now we notice that 1 power of L is going to cancel out there. Okay, so let's put that one first. We've got an L squared times a radius. Okay, then we've got P phi SGR. And then what have we got? In the denominator, we've got dH. Sorry, that's not written very nicely. That's a diffusion coefficient. dHRT. Okay, so let's put those numbers in. Let's give typical values for them. And again, remember, this is order of magnitude. So I'm going to look at an example that, for instance, is representative of hydrogen storage. So you put hydrogen underground. The hydrogen is generated from excess renewable energy. It's injected when there's excess energy, and then, say, in the winter, when it's needed to power a power station, for instance, or for a fuel cell, it's extracted. And as it does so, water from the underlying aquifer can move in and trap the hydrogen. But then Ostwald ripening can occur. So what's the time scale? So I already gave some of this away. L, I'm going to assume, is about 1 millimeter. I'm going to look at things at the sort of pore scale. Okay, a typical radius, say 10 microns. Okay, 10 to the minus 5 meters. These are just example values, right? Don't get too worried about it. Pressure. Atmospheric pressure is about 10 to the 5 pascals. We are deep underground. I'm going to look at something that's about 100 bars. So that's 10 to the 7 pascals. Okay, and that's large. You might say, well, what pressure is it? Is it the gas? Is it the water? The capillary pressure is of order of kilopascal. This is the absolute pressure, and it's the absolute pressure either imposed on the gas or on the water, and the difference is small. Right, so that's 10 to the 7 pascals. Porosity, say at 0.2. Residual saturation of 0.3. I'm going to do D and H a little bit later. Let's do R. R is the ideal gas constant, so it's 8.314 joules per Kelvin per mole. And T is the absolute temperature. Again, we're deep underground. This is absolute temperature. So 273 is 0. We're normally a little bit higher than that, so I'm going to say about 300 Kelvin. Okay? So what I'm going to do is now put those numbers in. I'm going to leave out DH just for the moment, because those are the properties that really depend on the particular gas. And I've always left something out, haven't I? There's a sigma that's gone missing. Okay, there's an interfacial tension as well. What's the interfacial tension between the gases? Well, at ambient condition, that's about 70 millinewtons per meter. At the high temperatures that you encounter underground, it can be a little bit lower. So I'm going to say 50 millinewtons per meter. That's 5 times 10 to the minus 2 newtons per meter. So this is all strict SI. So everything should allow us to get time in seconds. Okay, so let's put these numbers in. And D and H are going to come in a little bit. Okay, so L squared 10 to the minus 6, R 10 to the minus 5, P 10 to the plus 7, 5.2, SGR 0.3. Now let's look at the terms in the denominator. D, H we're leaving out. R, I'm not going to write 8.314. I'm not going to do this with a calculator. You can do that at home, but everything else is fairly hand-waving, literally. So let's just call that 8. Okay. We've got T is 300. And the sigma, yeah, we shouldn't leave it out, 5 times 10 to the minus 2. So let's see what we've got here. This becomes a 1. This becomes a 0.1. Okay, let's wrap up the powers of 10 at the top. Minus 6 minus 5, that's minus 11, plus 7, minus 4, minus 5, minus 6. So this is 2 times 10 to the minus 6. Okay, does that look right? And then that 2 can actually cancel here with the 8. So I can just make that 10 to the minus 6. Sorry, it's a bit of a mess, but we'll leave it like that. Okay, so that's 10 to the minus 6. And then what do we have at the bottom? We've got DH, and then we got a 400 times 5. So that's a 2000. 10 to the plus 3. And then that's 10 to the minus 2. Okay, so what do we have here? That's plus 1. So it's 10 to the minus 7. So it's 5 times 10 to the minus 8 over dH. So that, with the right units, should all be in seconds. So let's now talk about that, right? Let's now think about D and H. So diffusion coefficient. Hydrogen, actually, when it's dissolved, is not H+, right, which you might be familiar with. It's not protons. It is actually a hydrogen molecule dissolved in the water, but it's still very small. So it can, in fact, diffuse quite rapidly. On the other hand, we are looking at flow in a porous medium. So in fact, the diffusion coefficient, what I've done is I've corrected for porosity. It has a restricted diffusion, but it's still of around 10 to the minus 9. Okay, so something that diffuses a relatively small molecule dissolved in water normally has a diffusion coefficient about 10 to the minus 9 meters squared per second. Okay, so the diffusion coefficient I'm going to use here for hydrogen is 2 times 10 to the minus 9 meters squared per second. And this accounts for the porous medium. Then Henry's constant. Well, Henry's constant had these strange units. Remember, concentration was moles per meter cubed. So Henry's constant is moles per meter cubed per Pascal. So it's a little bit of a strange beast. Okay, so it's 7 times 10 to the minus 6 moles per meter cubed per Pascal. Okay, just check that. So that's 6, 7, that looks okay. So now let's put this in the equation and see what comes out. So we got 5 times 10 to the minus 8, 2 times 10 to the minus 9, okay, so let's look at the numbers. That's 5 over 14. I think we can deal with that. Now let's look at the powers of 10. That's 9 minus 6, so that's minus 15, goes the other way. Minus 8 plus 15, that's 10 to the 7th, isn't it? And 5, well, it could be 15, couldn't it? Right, or something like that. So this is roughly 3, 1/3, right? So it's then 3 times 10 to the 6 seconds, and that's about a month, right? Right, day is about 86,000 seconds. We got sort of a bit over a month, maybe a month, month and a half, something like that. So let's just think about the implications of that. Because if anything, this is an overestimate. It's enough flux to move all of the ganglia around instead of some subtle rearrangement. In fact, in experiments, we see rearrangement of the gas within a few days. Okay? But what this means is, imagine hydrogen storage as an example. The water moves in, traps the hydrogen, and then it rearranges at the millimeter scale over a period of a month. Well, the hydrogen storage is seasonal, so you'd be extracting the hydrogen, say, over the winter, over a period of about 6 months, and then re-injecting. So actually, there is time at the pore scale for the gas to rearrange. Okay, but what are the implications? Well, if we look at the time here, because Ostwald ripening is actually a diffusive process, you will notice that the time scales as length squared. So over larger scales, it seems like Ostwald ripening becomes irrelevant, but it is enough to rearrange the ganglia at the pore scale on the sort of timescales that we see in the subsurface. CO2 storage, that's even longer processes. You want the CO2 to stay underground for hundreds, if not thousands of years. Natural gas storage, again, can be seasonal. Natural gas production normally occurs over decades. So there's certainly enough time to rearrange on the pore scale. Put the numbers in, doesn't seem to make a difference at the field scale. So what are the implications? So I'm going to finish here. It's a really nice exercise in just putting 4 physical laws that you probably met before together to do something new. So that's what's nice about it. But the next video is going to look at the implications of this process on macroscopic flow properties. Thank you very much.